Great. So hi to everyone. I'd like to welcome Beatriz Gonzalez Del Rio, who's going to tell us a little bit about our work at Georgia Tech. Thanks a lot.
Great. So I would like to start by thanking TAG and the other organizers of the Electronic Structure Discussions Group for inviting me to give this talk about my present work here at Georgia Tech. My name is Beatriz Gonzalez, and I'm a postdoc in Professor Ramprasad's group at Georgia Institute of Technology. And my work here focuses on creating machine learning surrogate models to bypass the CONSAM equation in DFT and directly map the atomic configuration of any material to its electronic structure in an efficient manner, which significantly outstrips DFT in speed. So first, I would like to start by introducing the Ramprasad group, which is a large and increasing also diverse group of engineers and chemists and physicists who use different machine learning methods to advance material science and specifically polymer science. And to achieve this goal, we are supported by multiple agencies and also collaborate with various companies, as you can see here. And this is the web page of the group where you can see all our publications. So I will just briefly introduce like the main work done in the group, which is, as I said, in polymer informatics. And the essential elements of this polymer informatics ecosystem or pipeline are: first, we need the polymer data, which we obtained from high throughput calculations and also a lot of experimental data. And then once we have this data, we have to represent the polymers, meaning transforming them into what is called numerical fingerprints, which I will go into detail later, and to make them amenable to machine learning and artificial intelligence models. And then we have to develop these surrogate models for polymer property prediction and design new polymers with desired properties for specific applications. And lastly, we have an online or create an online user interface, which provides easy and quick public access to these developed surrogate models. Regarding this last point, the Ramprasad group has created an online platform called polymergenome.org, where you can deploy most of these models created by the group to predict a large variety of properties and of whatever polymer you desire. So for those that are interested in polymer science, this is maybe one interesting web page to go to. And here's an example of a given polymer where the user just inputs the SMILES string, even a sketch, and then you get some general information of the polymer. Also, you get a large amount of properties, and also you can get the structure of the polymer. And as I said, to create all these models, or most of them, we require high throughput DFT calculations. And especially also if you're using advanced techniques that also allow you to search the polymer space, which is being done right now in the group, to which this space is huge. And in order to find new candidates with optimal properties, once you find them, it's good to be able to perform DFT calculations to provide an initial validation of these findings before we send them to the experimentalists, because then creating this polymer is a laborious task. So this is the electronic structure discussion group. So I don't need to go much into detail, but in this aspect. But in DFT, for a given configuration of atoms, solving the CONSAM equation provides access to the electronic structure of the system in the form of the electronic charge density and the density of the states. And from these values, various atomistic properties can be computed. For example, the total energy and atomic forces, but also we can maybe from doing molecular dynamics, we can obtain also a variety of application relevant equilibrium material properties. Now, as I said here, I don't think I need to explain why, but the main bottleneck here is the high computational cost associated with solving the Ghosn equation. And which is a serious problem in many type of materials, and in our case for polymers, because even if we are just looking at the chain, this can be a very large, but also if you go to the crystal structure of the polymer or even amorphous polymers. So in order to overcome this limitation in general, the research community has recently started to use machine learning to bypass solving this Ghosn equation and directly predict the properties of interest, which gives rise to different types of models. So first one would be what's called machine learning property predictors, which go directly from the structure of your material to the property, which is what is normally done in our group within polymer genome. Then we have machine learning potentials and force fields, which are normally the ones used nowadays when performing what is called machine learning molecular dynamics. And lastly, in the last few years, the research community has started to focus on predicting the electronic structure using machine learning, developing what can be called machine learning DFT. Now, the Ramprasad group has experience creating machine learning models at all these three levels that we call in DFT, primary, secondary, and tertiary DFT output. And today, I will concentrate on our recent efforts in this last type of models, which are what I just said, the primary DFT output. So the first successful attempt within our group to predict the electronic structure used a grid-based approach with neural networks. Now, the protocol was applied to two different cases, polyethylene chains and aluminum slab. In the case of the charge density here, the models provided accurate predictions, but they require millions of grid points per configuration. And therefore, it was an expensive endeavor. With the neural network predicting the value at each grid point, therefore, each atomic configuration requires millions of predictions to obtain the entire charge density. Also, another important issue to take into account with machine learning models in general is their transferability, or lack of, actually. So the model was trained on, for example, the one that was trained on polyethylene chains. When applied to cases with double bonds, the performance decreases. So of course, once those configurations containing double bonds are included in the training, so here is depicted as model 2, the performance is greatly improved. Now, this is the parity plot between the actual DFT charge density and the machine learned predicted charge density. So you can see that once we include those configurations that contain these double bonds, then the performance improves. So this showcases the importance of having a diverse data set for your training, which can be a difficult task if for each atomic configuration, you already have millions of grid points that you have to use during training. Now, if using a grid-based approach for the density is already expensive, it is so much more if for the case of the density of states. Now, if we look at the charge density as the spatial distribution of the electrons, the density of states can be seen as the energy distribution of the electrons, or charge density. Now, to describe it in terms of the grid points, we first have to separate the density of states into energy bins, which in this work were of 0.1 eV. And then within each energy bin, we need to obtain the partial charge density, which is the distribution of the charge density within that energy range. So as you can see in practice, the density of states implies learning and predicting multiple instances, in a way, of the charge density in a grid of millions of points, which of course makes the entire task extremely expensive here. So as you can see in this graph, which compares the computational cost between DFT and using machine learning, here is in the best case scenario where it is scaled quadratically. Even though machine learning decreases the cost, most of the time is employed in fingerprinting, actually, which, as I said, we will see more in detail what that is. But in fingerprinting, all these millions of grid points that we have for each configuration. Therefore, our first goal was to change the entire protocol from a grid point to an atom-based approach to speed up the entire training and prediction process. And within this goal, we first focused on the density of states, as it was the most expensive of them. Okay, so for our agenda for today's talk, we can graphically describe it by the entire scheme of the atom-based neural network density of states protocol, and I will go through each step, describing in detail each concept and results. So this scheme, although shown here with the specifics of the problem at hand, which is the density of states, can be easily generalized to other property predictions, as we will see at the end of the talk. So the first step when creating a machine learning model for any property prediction is creating or the gathering of the database and its fingerprinting. So let's leave right now for a second the database aside and go into what is fingerprinting and how to choose what type of fingerprints we should use for our problem. So to put it simply, fingerprinting is representing numerically the material. Now, in order to choose the best numerical representation, you need to know the problem and the target property. And depending on the problem and the accuracy required for the prediction, the fingerprint can be defined at different levels of granularity here. For example, if the goal is to obtain a high-level understanding of the factors underlying a complex phenomenon, such as the mechanical or electrical strength of a material, and the prediction accuracy is not critical, then the fingerprint may be defined at a gross level in terms of general attributes of the atoms the materials is made up of, as well as other relevant properties such as the band gap, or higher level structural features such as the typical grain size. Now, if the goal is to predict specific properties at a reasonable level of accuracy, okay. Yeah, sorry. So if the goal is to predict specific properties at a reasonable level of accuracy across a wide chemical space, such as the dielectric constant or the glass transition temperature of a polymer, then the fingerprints will require information pertaining key atomic level structural fragments that control such properties. And finally, if the extreme or chemical accuracy is required, I don't know, my computer is kind of, okay. If extreme or chemical accuracy is required, such as in the case of the electronic structure properties or total energies or atomic forces, then their fingerprint has to be fine enough to encode details of the atomic level structural information with sub-angstrom resolution. So as a rule of thumb, the finer the fingerprint, the greater the expected accuracy, but also the more laborious and data intensive and less conceptual the learning framework is going to be. So in our case, we require to use the highest level of accuracy and detail in the description of our atomic configurations, and therefore we need to use atomic level fingerprints. So to first develop the entire protocol, we chose a data set containing just one single element, but diverse enough. So in our case, we chose carbon, and as the structures, we went with graphene-derived allotropes. Also, we created two different data sets to test the transferability of the model, two configurations which contain defects and also higher disordered structures. Additionally, to have a large amount of configuration of each structure, we perform molecular dynamics simulations at 300 and 600 Kelvin, and then chose 200 random snapshots from it. And to fingerprint all these configurations, we use the group's previously developed fingerprint expressions, but instead of fingerprinting the environment of each grid point, we center the fingerprints at each atom. As such, if we want to create the fingerprints describing the atomic environment of atom G here, we can create a scalar fingerprint, which takes the form of a Gaussian function, which depends on the distance between the atom G and its neighbor I, and has a width, which is sigma k, which is a variable that we can specify. Also, to take into account the decay of the effect from faraway neighbors, we introduce a decay function here, which takes the form of a cosine decay and is null after a given radius, which is also another variable that we have to adjust. And similarly, we can define a vector type fingerprint as well as a tensor-like fingerprint, where here alpha and beta are the different components of the vector position of the neighboring atoms with respect to the central atom that is fingerprinted. Now, this type of expression using Gaussians, along with a cutoff function, is very common in many other types of atomic fingerprints, such as the Veller-Parinello fingerprints. Also, there are other types of common fingerprints, such as the smooth overlap of atomic position or SOAP, or the Gaussian approximation potentials, which are a very type of successful machine learned potentials to do molecular dynamics. Now, one important thing when creating fingerprints is that they need to comply with the invariances of the target property. Now, in our case, the density of states is translational, permutational, and rotational invariant. The translation invariance is introduced by using the distance between the atoms and not the position. And the permutation invariance is introduced by summing over all neighbors. Now, regarding the rotational invariance, even though the scalar fingerprint complies with it, the vector and tensor fingerprints do not. However, we can develop other expressions which are rotationally invariant, as we can see here. Lastly, once we have each configuration fingerprinted, we can perform a principal component analysis here, which shows how the fingerprint features of each type of structures span a large region of configurational space. Now here I am showing the first two principal components, which simply show the two features of the fingerprints which vary the most. And it's nice to see here how different configurations from the same structure are grouped together. And here in blue, for example, are the cases with high disorder. So we can see how they actually are in a slightly different region of a space than the configuration at 300 Kelvin, for example. So once we have the data set and the configurations fingerprinted, it's time to choose our machine learning model and train it. Now, there is a large variety of machine learning models out there, depending on the problem at hand. Now, in our case, we are interested in regression models as we want to predict values versus, for example, classifying. And as we're working with complex problems like predicting the electronic structure, the best approach is to use nonlinear regression models. Two of the most common types of machine learning models used when creating machine learning force fields, potentials, or even prediction of some electronic structure properties are the Gaussian process regression model and neural networks. Now, the GPR is a kernel-based approach where the prediction is made in terms of the distance of the features of the material to be predicted to the known features used in the dataset during training. It is a powerful model, but can be expensive to train and predict when the dataset starts being very large. In this case, neural networks are perfect for large datasets. In fact, they require them and can be extremely flexible, which is a good thing, but has to be taken with care to avoid overfitting, which we will see in a minute. Now, in our case, we chose neural networks, and the main ingredient is what we call a perceptron or node, which functions by multiplying each input by weight. And also you can add a bias, and then the output is passed through what is called an activation function. Now, in our specific architecture, the fingerprints were given as input to a dense layer, it's called, with 300 perceptrons or nodes. And then we use the rectified linear unit activation function, or ReLU. And here we can see some of the most common activation functions. And to choose among them, you need to think about the target property you want to predict. Now, in our case, the density of states only takes positive or zero values. So we choose the ReLU activation function because if it's negative, it's going to make it zero, and whatever positive value is going to leave it as it is. And then we added a dropout layer, which what it does is that instead of having all the nodes active during training, each node is going to have a probability X of being dead. Here, such probability that we used was 0.1 or 10%. Now, the advantage of using dropout is twofold. First, it makes the model more robust as it works as a regularization technique. Now, regularization is used to reduce the overfitting that can happen due to the high flexibility of neural networks. So in order to see if we have this overfitting, one thing that is normally done when training neural networks is to split the training configurations that you have in your data set into what is going to be actually used for training and the ones that are going to be used for validation. And normally this split is done into a 90-10 or 80-20 splitting. Now, during training, we will look at the loss or the error for the training set, but also for the validation set. And here's an example. And basically, even though the model will adapt the weights so as to minimize the error made in the training, the error for the validation allows us to see when the model starts to overfit those weights, because the training error will continue to decrease, whereas the validation, or here is called generalization error, will start to increase, or it can stop decreasing also. So at that point, in this point where this starts to happen, is where we do what is called early stopping. and meaning that we will use the weights that the model has at that specific point, and that's it. And the second advantage of using a dropout is using it also during prediction, because we can use it to get a value for the uncertainty of our prediction. Now, in our model, we repeated this set 5 times. So we have 5 dense layers. And then as the last layer, we had a one-dimensional convolutional layer, which has the task of smoothing out the final density of states curve. Here I'm showing a 2D convolutional layer. In our case, it's just 1D. So basically, instead of taking this 2-dimensional area, it would be just 1-dimensional. And basically what it does is similar to a perceptron, but it only takes into account the values of a given number of inputs. So instead of taking from all of them, it's just from a range of them. Here we said the length is 3. And that is the model basically. And then the last one is also another final reload layer. So there are some other details regarding the optimizer, the learning rate, and some other regularizations, but this is the essence. If for more details, you can go to the paper. And this is our learning curves, and we use the mean square error as the error function, and we can see how the validation loss decays with the training until at some point at which it stops improving. So at the point where it stops decaying, that's where we did this early stopping technique and just took the weights at that point. And finally, once we have our model built, so one thing is that this model that I show here, what it does is, as I said, we give us input the fingerprint of each atom. It goes through all these 5 layers, the convolutional layer, and gives us output the density of states for that atom. And then we give us input on the other atom, and it goes through the same model and gives us output the density of states for that atom. And then what we do is sum all contributions, and then we obtain the total density of states. So as I said, once we have our model built and trained, we need to evaluate its performance. And we sum it, we get the total density of states. Also, another thing we did then is to compute the cumulative sum in order to be able to improve the Fermi level. When we calculate the Fermi level from the predicted density of states, we also wanted to be sure that the error was minimized there. So that's why we also added the cumulative sum of the density of states, of the predicted density of states when comparing to the target data during training. So once trained, we can see the model predicted density of states on the test configurations. So another thing is, when we evaluate the performance, we do it on some configurations that were left out. So they were what is called test configurations. They weren't used either in the training nor in the validation. So it's totally new. And we can see that it predicts them with high accuracy for all the structure types. And as an example here, I'm showing the performance on test configurations for graphene, C60, and 2 carbon nanotubes, C99 and C80, where here the predicted dose is in red, follows very closely the reference DFT density of states, which is in blue. And likewise, the Fermi level computed from the cumulative integral of the predicted dose, which here we show in dashed red line, coincides with the DFT Fermi level, which is shown in dashed blue line. Now, the histogram of the error in the calculated Fermi level from the predicted density of states follows a Gaussian distribution where the instances with a high error drastically decay after 0.2 eV. And also then we have to test the transferability. to new environments, which we know, and I already said at the beginning, that's one issue with machine learning models in general. They will not perform that well in transferability tests, especially if the transferability is to completely new environments. So here, our data set, as you recall, had some, was graphene with some defects, and also we included configurations, snapshots from molecular dynamic runs, but at 2000 Kelvin. So there was higher disorder, but it still was from C60 or the carbon nanotubes. So to test the transferability to these new environments and also the capability of the model for systematic improvement. So we first tested the performance of the model trained on the dataset 1 as the beginning, which we will refer to the model as model 1. And we tested it on configurations of dataset 2. And afterwards evaluated the improvement on the predictions once we include this data set during training, and that's model 2. So if we look at the root mean square error and the mean absolute error in the Fermi level calculation with model 1, shown here by the gray bars, you can see that there is a worse performance on dataset 2, both for the defects and the highly disordered structures. But given the considerable difference between the atomic environments and the types of, actually different types of carbon hybridization between the dataset 1 and the dataset 2, the results are still surprisingly good. I mean, they're worse, but not that much. Once the model is also trained on dataset 2, which we show here with the dark red bars, there is a drastic error decrease on the prediction on the structures of dataset 2, especially, of course, as well as a slight error reduction on the dataset 1 as well. So these results illustrate the capability of the model for systematic improvement as the dataset size is expanded, even with entirely new information. And lastly, the Van energy computed as the cumulative integral of the product between the level occupation and its energy up to the Fermi level has a mean absolute error below the chemical accuracy threshold for all cases. So using model 2. So you can see that it's below 0.043 EV per atom, which would be 1 kilocal per mole, basically. Great. So after the successful results that I've shown for the graphene-derived allotropes, the next step is to expand the protocol to multi-elemental systems. And to do so, during the fingerprinting step, we will differentiate between atoms of element A and those of element B. Let's say we have 2 elements here. And we calculate their fingerprints of each atom by concatenating the fingerprints describing the atomic environment created by atoms of type A to the fingerprints defining the atomic environment created by atoms of type B for each type of atom. So each type of elements will have their own, also that's another important thing, will have their own submodel. So that's why I put it different colors here, which we will predict the density of states per atom for each one, obtaining the total density of states by, here is summing all contributions. So we can actually think of this as like a pseudo potential, basically. So if we have, this will be the pseudo potential for atom of type A, and then a different pseudo potential for atom of type B, in a way. Now, as I said before, this scheme could also be applied to any other extensive property, right? So which depends on the amount of matter or atoms that we have. So so we predicted for each atom and then sum the contributions from all the atoms, such, for example, like the total energy. So here we could have, like, instead of all these perceptrons, it would just end on one perceptron, and we could have the energy for that atom. Or you can have it for the electron density, what you want. and then sum all of it, because the target property we just have in the case of the energy is the total energy is just one value. We don't have the energy per atom. But for example, for the cases of atomic forces, we actually have the value for each atom. So that's actually much easier because we just predict the forces. Here it would be like 3 perceptrons at the end, like each component of the force, and then we actually have the target value for each one. So that would be an easier, but that's how it works. Now, the main research line in the Rampersad group is, as I said at the beginning, is polymer informatics. So a natural extension of our work is to a database comprised of various configurations of polymers. So right now we concentrated on hydrocarbon polymers, and our database right now, the work that we're finishing right now and preparing for submission, contains 150 different polymer chains. And we use this neural network approach for the density of states, and here we can see that we obtain pretty good comparison. We followed the same scheme as for the carbon database. We perform molecular dynamics of each chain at 300 Kelvin to obtain different types of configurations, and then some of them were left out for the test set. The other one is for training, and within the training, we did this splitting between the actual training and the validation. And this is the performance always when I show it, is for the test set. So it's totally unseen configurations. And here we can see that here I'm showing also the valence band and the conduction band, and even when they're very different, we also obtain good results. There is some modifications with respect to some details different with respect to the carbon work on the graphene derived allotropes, but in essence is the same. Yeah, and additionally, we have followed a similar neural network protocol to create an atom-based charge density, which was the other thing that was left, right, to get the entire electronic structure of the system. And what we did is use this neural network protocol, atom-based, to predict the charge density of the representation on basis functions, which can either be Gaussian type orbitals or Slater type orbitals. We have seen that Gaussian type orbitals work better in this description. Now, this protocol is based on an atom-based decomposition, and not only allows the user to predict the atom's contribution, each atom's contribution to the total charge density, but also the angular momentum decomposition of the charge density. So this is for example, this change here, and you can see like for the S, the P, and the D type of orbitals. Now, it has to be said that this idea of an atom-based decomposition of the charge density is not novel and was previously employed by Fabricio and co-workers. They use a GPR model and a database of dimers containing carbon, hydrogen, oxygen, and nitrogen. So their approach, actually, there are some differences. So I'm going to briefly explain what their approach was and then some difference with ours. So their approach requires an initial decomposition into a specific basis set. And here you can see all the basis sets they try. This is for the case of a water molecule. And they saw that the best performing type of basis sets is the ones called like the resolution of identity type, which are used to actually fit the density. Now, this error metrics here give the percentage error with respect to the total amount of electrons in your system. And you can see that is the decomposition using the resolution of identity gives you like around 0.3% error. Once they have this decomposition done, so once they have the values multiplying the basis function, the model, what is going to do, the GPR model is going to predict these components of the decomposition. And the error then that they show here, this is the error of the model that they train, This error is with respect to the already decomposed density. So to this error, you would have to add the error of this previous error that they were making. And even though they obtain very low error percentage always, it's important to note that they are using the core density also. So it's not just the valence density. And because the valence density is the one where most of the error is going to come from because of this delocalization. So that's one thing. So then the total number of electrons that they are dividing to get the percentage error is much higher as if they were just using the valence electrons. However, another thing is that once they go to larger molecules here, this error significantly increases, which poses concerns regarding the transferability of this model to even larger systems, because at the end, that's what we're interested to use it for very large systems where DFT cannot be used. Now, in comparison, our model compares directly to the DFT density. That's one thing when doing the prediction and the training. When doing the training of our model, it directly, the target value is the DFT density, not the already decomposed density. And also, it does not require a previous decomposition or in fact, any previously created basis function, as the model is going to learn the optimal basis function. Also, our model only employs the valence density, and the error percentage that we get is around 0.9 and 1.3, which is similar to the values that we were getting here. But then again, this is using also the core electrons. So if they were to just use the valence electrons, probably it would be much higher. Also, another thing to take into account is that it is we obtain very consistent performance. As I said, it's between 0.5 and 1.3% error. And that includes when we even test our model on crystalline polymers, which are not included at all in our system for training. We only have chains. So it is very robust and transferable model. And lastly, one thing that's very important is that it can be used with molecules and periodic systems alike, which the previous model by Fabrice and co-workers could only be applied to molecules. So together, once we combine both protocols, they can provide access to both the spatial and the energy distribution of the electronic structure and give us a complete neural network DFT emulator. So in summary, we have developed a density of states predictor, which outperforms DFT in times and preserves its accuracy. The neural network density of states can be easily extended, as I showed, to multi-elemental systems. And the same atom-based protocol can also be implemented to learn the charge density. Future work includes combining these two protocols to obtain this complete DFT emulator to then, by including also the prediction of the total energy and the forces. We are also right now working on extending it to nitrogen and oxygen element containing polymers. And also we want to create a user-friendly package to train and use already available models for molecular dynamics simulations for the general public, because one thing is that normally all these models are used and developed by the people who actually create them. So it is good to create these friendly usage packages so that people who are not that experienced in developing these models, but we want to employ them to study different systems, can do so easily. And finally, I would like to thank all of you and my collaborators in this work, Dr. Christopher Queneth and Juan Trang, and also Professor Ramprasad and the entire Ramprasad group, and also the funding for the National Science Foundation. Thank you.